So we're going through some of the parts in the slide now where we've got some questions which are in the context of being projectiles. Now there is a bit of a difference, I think, in one of these questions. So we might come to that in a minute, but projectiles are a case of really doing what we've just been doing. Okay, so chapter 6, chapter 8, this part's really, really similar. So let's have a go. A ball is struck by a racket from point A, and point A here we can see is off the floor. Its position is 20J. So the way that I'm probably going to handle this bit here, I might even want to just kind of highlight this to make sure I come back to it, is I will just add this into things at the end most of the time. The ball, immediately after being struck, the ball has a velocity. So I think that's U. So that's 5-8, because that's the start, so it's going to be the start of a journey. After being struck, travels freely until it hits the ground. Yep. Find the speed. Speed, 1.5 after being struck. Okay, so if it says travels freely under gravity, that's the only clue that I've really got here. So this means it's going to be about constant acceleration. So I want to be thinking in that again. I've got U. I do actually have A as well. So A, what's A then? A would be 0, because horizontally we assume that there's no acceleration. And A, because this is positive, A must be minus 9.8. So we do actually know A. We've been given a t value, and they want to know something about velocity. So that means we're going to use the same one we've been using many, many times. V equals U plus AT. So we're going to do 5-8 plus 1.5 lots of 0 minus 9.8. So we're going to get these numbers. Okay, and that gives you 5 and minus 6.7. And then what we're going to do there is we're going to recognize that means that it's going 5 to the right, 6 down, and so on. But really, the speed is the diagonal on that one. Okay, so the magnitude of the velocity is when you do square root of 5 squared. I'm just going to do the 6.7 as that, and that gives you 8.4 meters per second. Okay, so that's how you would do the part A. Now, let's make that a little bit smaller, and then we can zoom in a little bit more. So, what are we doing next? Find an expression for the position vector R. So in the world of vectors, tend to use R more instead of S, relative to the origin. So they want like a general way of expressing it. So let's say R equals UT plus half AT squared. How do I know to use that one? Well, it's the one that pretty much always comes up, isn't it, for projectiles? It always comes up because you tend to be given U, you have found out, or you get given A, and T is generalized. So that's why this one's so useful. So R is going to be equal to 5-8. I can recycle that again. Then I'm going to keep this in terms of T, a half of these numbers. So that is a 0 and a minus 4.9 T squared. And if I tidy that up just a touch, I would get 5T and then 8T minus 4.9 T squared. Now, this is why I've highlighted something, because it means I'm going to come back. So this just tells you the difference compared to where it was before, right? So it tells you that, you know, you're going from here to some other point on the journey. But this wanted to know relative to the origin. So the origin's down here. So what's the connection to the origin? Well, the origin is just 20 meters more of a gap in the J direction. Okay, so for example, how to do this without getting too confusing. This point here is 20, right? But at the moment, if we put T equals 0 in here, we'll get 0. So we need to add on 20. Up here, let's pretend this might be 25. meters from the ground. But at the moment, it would just give you, say, 5 when you put the correct number in. So again, all of these numbers need to be uplifted by 20. Okay, so we need to remember to put that part in there as well. So that just sort of comes later outside of SUVAT. And the reason why, one more time, is because the S or R in this case, it tells you the displacement, it tells you the difference in the journey. It doesn't actually like take into account that it was offset, that it started higher up off the ground. Okay, and hence determine the distance OB. So OB, right, not AB, just OB. So OB is the horizontal distance that it travels, isn't it? So when you have something hitting the floor, the best thing to do usually is find out the t value when it hits the floor. So we want to solve this bit first. Yeah, we want to do 8t minus 4.9t squared plus 20, because this says the distance above the ground. We want to know when the distance above the ground is 0. If you do that, you get a number very, very close to 3. And then there's a bit of a trick here. So if you want to know how far it goes horizontally, you just use the horizontal one, which is in here, and then notice that it's a case of just doing 5 times however long it traveled. And you did this in projectiles from before. So 5 lots, please, of that 2.995. And that gives us, I've got it just 2 significant figures here, so 15 meters. Okay, so some overlap there with chapter 6. Some of the things that are less obvious would be like adding this 20 later. I think that's a lot less obvious. But yeah, a lot of similarities hopefully at the same time. So that's how you do this question here.